All right, guys, welcome to lesson 4.6. We're going to continue our chat about differentiability. We call this part 2. We're going to talk more about piecewise functions, but I'm going to show you guys a slightly different kind of question. Last time when we talked about differentiability with piecewise functions, the question was, is it differentiable at a given point? The question we're going to look at today is how can you make this function differentiable? So it's a little bit of a different question. And then second, we'll be applying these principles to absolute value functions a little bit. So all that being said, let's go ahead and jump in and take a look at our first example here. So before we begin an example of today's new lesson, I want to review an older question with you guys a little bit. And I don't want you guys to write this, I just want you to review it. So I gave you guys a piecewise function in the past with a missing number and represented by the letter A. And the goal was that we wanted you to find the value of A that would make this piecewise function continuous. Well, as you guys know, in order for a piecewise function to be continuous, the function has to exist at that point. Since there's an equal sign, it exists there. But we also need the limit from the left and the right to match so that the limit exists. And so what we do then is we go ahead and we find the limit from the left, which would be x squared plus ax. And we find the limit from the right, which would be 2x plus 3. Where we plug in this boundary point where they connect, which is 1. So if you were to plug in 1 there, you would end up getting 1 plus a equals 2 plus 3. And if you solve for a, you're going to end up with 4. And so a would have to equal 4 in order for these two pieces to connect, and we would end up with a continuous function, right? That's something that we did a little while back. Well, we're going to do something very similar today, but it's going to involve finding a value of a that makes the function differentiable, okay? And this is going to look a little bit like what we did last class, and it's also going to involve this stuff here. So let's go ahead and take a look at an example where that sort of stuff comes into play. So here's my piecewise function now, and this time we actually want to find two values, a and b, so that the piecewise function is differentiable. Not just continuous, but differentiable. But as you guys know, at this point, that if you want to find or make a function differentiable, then it also has to be continuous. So our first task is going to be to make sure that it's continuous. And that part of our task is not going to be new. What we do is we want to make sure that the limit as we approach 1 from the left and the limit as we approach 1 from the right are the same. And that will make these two pieces connect together in the way that we want. Now from the left, that's going to be the piece that's 3 minus x, and from the right, that's going to be the piece that's ax squared plus bx. And we need to force them to be equal to each other. So let's do that. We're going to plug in 1, which is going to be 3 minus 1 on this side. And on this side, it's going to be a times 1 squared plus b times 1. Which is just going to end up giving us 2 is equal to a plus b. Now that doesn't tell me what a and b are, but it does tell me something about a and b. Whatever those numbers are, when you add them together, they have to equal 2. So I know that much. But we have a little bit more work to do now, because once again, I don't just want a and b. I don't want this function to just be continuous. I want it to be differentiable. And in order for it to be differentiable, it does need to be continuous, but we need something a little bit more for it to be differentiable. We also need it to be, as we remember from last class, smooth. And so that means I would not only want to find the limit from the left and right of 1 with the original function, but I also want to find the limit from the left and right with the derivative of this function. So the derivative of this is negative 1. Okay? Now the derivative of this, mind you, we're finding the derivative with respect to x. Okay? So for a minute here, I'm just going to make up some numbers for a and b really quick. I don't want you guys to write this. I want you guys just to watch though. Okay? So let's say instead of a and b, let's say it was 2 and 3. So instead of ax squared plus b, it's going to be 2x squared plus 3x, right? If we found the derivative, what would we do? We would multiply the 2 to the front, right? And then we would take 1 away from the power. And for this one, we would just, to take the derivative of that, it's just going to be 3. We would just get rid of the x, right? But as you can see in this case, we're dealing with a, which it is a number. The problem is we just don't know what that number is. So I'm going to get rid of the 2, and I'm going to get rid of the 3 now that we know how to find the derivative. And let's put back what they were. Now, they really are a and b, right? So when you take the derivative, you're going to treat the a and b just like their regular old constants. So that would look like this. Okay? So if you're taking the derivative of ax squared plus b, you're going to multiply the 2 to the front of the a, and you're going to take 1 off the power. And for this one, since it's just a number in front of an x, when you take the derivative of it, the x just goes away and you're left with b. All right? So it's a little bit weird when you're taking derivatives with letters instead of numbers, so that's why I wanted to spend some time on that, but there you go. So the derivative of this left side here, 3 minus x, is negative 1. And the derivative of the right side, as we've already done, is 2ax plus b. Okay? And once again, in order for this to be smooth, these need to be equal to each other. So the slope from the left needs to equal the slope from the right. All right, so we do our direct substitution now. On this side, there's really nowhere for me to plug the 1 into. So the answer is just going to be the number that we have there, which is negative 1. And on the right side, if we plug in our 1, we're going to end up with 2 times a times 1 plus b. And from that, we could see that it's just going to be 2a plus b, because when you multiply something by 1, it stays the same. And now we have 2 facts. We don't have our answer yet, but we have 2 facts that are very helpful. In order for it to be continuous, which is also a prerequisite for differentiability, we know that a plus b has to equal 2. But it also needs to be smooth, and for that to happen, we know now that 2 times a plus b has to make negative 1. What we have now, if I want to actually figure out what a and b are, I need to find out a value for a and b that not only works for this one, but also works for this one at the same time. And that's what we call a system of equations, which is a little something you might remember from Algebra 1 or 2. Okay, so let's go ahead and solve the system. Now, there's different ways to solve systems of equations. Let's talk about, I think I'm going to give you one way that I think is maybe going to be a little bit more useful for you in this particular lesson. And we're going to go with the method called substitution method. Okay, so with the substitution method, what you want to do is you want to get one of the variables by itself. So for instance, over here, I'm going to get the b by itself. I'm going to minus a on both sides. That's going to give me 2 minus a equals b. All right. Now, why would I do that? Well, by getting the b by itself, I can replace b with 2 minus a because they're equal. And that's exactly what I'm going to do over here. I'm going to replace the b. I'm going to replace that b there with 2 minus a. Okay? So this is what we call the substitution method for a system of equations. Okay, so step 1 is to get a variable by itself. It doesn't matter which one you do. I could have gotten the a by itself instead of the b, but I chose to get the b by itself. Little word of advice when you do this, make sure you pick one that results in no fractions if that's possible. Fractions aren't fun. Step 2, we substitute. So since b is equal to 2 minus a, I can replace this b with 2 minus a. And then after that, you solve. So in this case, if I were to try to solve this equation up here, I would combine my like terms, 2a with negative a. That's going to give me 1 positive a. And then I would minus the 2 on both sides. Okay. Once you have a solved for, you just go back and you plug that value of a into one of your original 2 equations and solve. So plug and solve for b. So, for instance, I'm going to take my 2 equals a plus b. I'm going to take that, And now that I know that a equals -3, I'm just going to replace a with -3, and that's going to allow me to solve for b. And so there's my two answers. I got my final result. A would have to be -3, and b would have to be 5. So let's review the process for this problem here. I know that these could be a little bit tricky and challenging because there's a lot of steps in them, okay? So the first thing you need to do is you need to create one equation. Actually, let me see if I can zoom out a little bit. There we go. So the first thing that you're going to do is you're going to create one equation by forcing the functions to be continuous. And from that I got here, right? Then you're going to create another function by forcing the functions, by forcing the derivatives to be equal. And then after that, the rest of this was solving a system of equations by using the substitution method. So it's a three-step process. Make one equation by making it be continuous, make another equation by making it smooth, and step 3, solve the system of equations to get your answer. So a lot of algebra there. Let's go ahead and have you guys try something like this, though. Here we go. So why don't we treat this one like a guided practice. I want you guys to do the first step, which is to create an equation by forcing them to become continuous. So go ahead and pause the video here and see if you guys can get that done. And then when you unpause it, you'll see what your first equation should have come out looking like. Okay, so this is what you guys have here. Now you might have stopped here like I did, or you could have gone a little bit further. This is fine, but I would personally like to fix it up a little bit and make it look cleaner. Now you don't have to. You'll still be able to solve it if you don't. But for me, for instance, I would want to minus these b's on both sides just so we end up with something a little easier to look at. And then if you divide both sides by -1, you've already got your answer there for A. A would have to be 1, so that's kind of cool. All right, but now I want you guys to do the second step. The second step is we want to create another equation by forcing it to become smooth. So why don't you guys pause the video here and see if you guys can write another equation that will force the equation to come out with a smooth connection. So there's our second one. Now, there's a couple of tricky parts here. First thing, you have to take the derivative of this. Now, when you take the derivative of that, you just take the a, which is in front of the x, so you get a, and then the derivative of b, since it's just a constant, even though we don't know what it is, it just goes away. So the derivative of ax plus b is just a. Next, we find the derivative of this, so you'd multiply the 2 times the front of the b, which would give you this, and then you subtract 1 from the power, which leaves you with x to the first power. And then, of course, the derivative of -1 is gone, so we don't put anything for that. So there's your derivative. Then you do your direct substitution. Now, there's nowhere to plug this -1 into. You plug it in for x, right? And there's no x's here. So the answer for that one is just going to be a when you do your direct substitution. But for this one, when you plug in your -1 for x, you get 2b times -1, which makes -2b. All right, so now we have two equations, right? I have a equals 1 and a equals -2b. All right, so I want you guys to do the third step, which is to solve that system. Now, we've already got a solved for, so that kind of makes it a little bit easier. But go ahead and finish the problem, see if you can find both values for a and for b. When you unpause the video, you'll see the solution. All right, so there you guys have it. Like I said, we already know a is 1, so at this point, since we could skip the first step, which is get a variable by itself, because we already have a variable by itself. We have a equals 1. So I just need to take that 1 and plug it in for a in the other equation over here. It was a equals -2b, but if I replace the a with 1, I get 1 equals -2b. And then division to solve for b gives me -1/2. So we're pretty much home free there. We have our two values of a and b that will force this function to come out to be differentiable at the value where the piecewise functions are joined. All right, so let's go ahead and take a look at another. All right, so here's another one for you guys. Go ahead and see if you guys can find the values of a and b that will force this piecewise function to be differentiable. I'll let you guys go ahead and handle all three steps this time on your own, and when you unpause the video, you'll see the solution. All right, so I'll let you guys go ahead and study that, but you should have gotten negative 23 for A and 3 for B. Here's how you would find an equation for continuity. Here's how you would find an equation for smoothness. And solving the system would give you that. So there's your 3 steps for student practice 2. All right, so I want to talk to you guys about how do you find the slope of an absolute value function. Now, we've already done this before. Now, you guys don't need to write this slide. Okay, this is a review question. Back in Unit 1, we talked about how to find the slope of absolute value functions. So it's pretty straightforward. We just have to remember our formula. So the formula for finding the derivative of an absolute value function is as follows. It's going to be the original problem in absolute value bars. And on the top, you'll have whatever's on the inside there. Now, you'll also need to multiply it by the derivative of the inside, because this is a chain rule. So the derivative of the inside is 2. So there it is. So this is the basic absolute value derivative process here, but if you have a chain rule, in other words, you have something else on the inside, you do need to multiply by the derivative of the inside. So if you wanted to find f prime of 3, what you would do is you just plug 3 into this derivative. And you'd get your answer. So 6 minus 5 is 1. And the absolute value of 1 on the bottom is going to be 1. So this whole thing here just becomes 1 times 2, which is 2. Okay? So that's how you find the derivative of an absolute value function. But absolute value functions, as you guys might remember from Algebra 1, 2, or even pre-calculus, absolute value functions have cusps. When you graph them, they look like this, right? Sometimes they bend. Usually in classes prior to this one, they just focus on the ones that straight up look like a V shape. But they don't have to look like a V shape. The point is basically it just causes your graph to become have a cusp in it. Okay? So when we're being asked to find the derivative of an absolute value function, it doesn't matter that the little trick we talked about will work for any point here. What I just did will help you find the derivative of any point on your absolute value function unless it's at a cusp. Okay? If it's at a cusp, then that derivative is not going to exist because derivatives don't exist at cusps, right? But so like what would the cusp be for this problem? Well, the cusp happens anytime the inside equals 0. So if I solve for x here, I would find out that that's at x equals 5/2. So if I asked you guys to find f prime of 5/2, well, since that's what makes the inside 0, that's where the cusp will be at, and therefore this would not exist. But I could ask you guys another type of question. I could ask you guys to find what is the slope as I approach 5/2 from the right? Because there is a slope on the left side and there's also a slope on the right side. The problem is that they just don't match. So even though this doesn't have an answer, the slope from the left and the slope from the right exist. And so we want to know how to find the slope from the left and the right sometimes, and that's what our next problem is going to be looking at. So don't forget this old little rule here, because if they ever ask you just to find a derivative, well, of an absolute value function, that's how you do it. Nice little formula. You don't really need to worry about it too much. But if they're ever asking you to find the slope at a cusp, which is where the inside equals 0, well, for those particular points, the derivative itself won't exist, but you may need to be able to find the limit from the left and the right, and that's what we're going to look at now. So let's go ahead and take a look at an example of that sort. So example, I think I'm on example 2 now, aren't I? All right, so here's my function. I'm going to say that g of x is equal to the absolute value of x squared minus 3x plus 2. Okay? So let's begin here. So the first thing I want us to do is I want us to rewrite this as a piecewise function. Now we've done this before, but it's been a while, so let's review that process. Whenever we're doing calculus with absolute value functions, it's usually nice to just rewrite them as piecewise functions. In this case, that's definitely going to be the case. So here we go. How do you do that? Well, the first thing is you set the inside equal to 0. Actually, I'll just write this. And solve. Okay? So I'm going to take the inside there, which is x squared minus 3x plus 2, whatever's inside the absolute value bars, and I'm going to set it equal to 0. And now we have to factor again, and that's not going to go away. We've got to keep knowing how to factor, so make sure you guys do know how to factor. When I factor this, I end up with x minus 2 and x minus 1. We set each one of these things equal to 0, and we solve. So these are the two values of x that make the inside equal 0. Now, why would I want to find that? That's because that's where the cusps are located. Remember how I told you whatever makes the inside equal 0, that's where a cusp is at? So this finds where the cusps are. So that helps us find our cusps. So this graph, if I were to graph this function, would have a cusp at x equals 2, and it would also have a cusp at x equals 1. But that's kind of beside the point. For now, just hold on to the fact that the first step is to set the inside equal to 0. After that, we do our number line test. Okay, so we set up a number line with those two x values on there. We have x equals 1, and we have x equals 2. And what we're going to do is we're going to plug some numbers in from each one of these intervals to see whether it will cause a change in the signs of the function or not. Okay, so let's go ahead and do g of, let's pick a number to the left of 1, like 0 is a good one. We'll pick a number to the right of 2, like 3, and then we need a number between 1 and 2, and unfortunately that's just going to be a fraction, so I'm going to go with a half, 1.5 there. So we're going to plug in 0, 1.5, and 3 into this expression up here, and we're going to see what we get. Okay? Now, as you guys can see here, after I plug in 0, I get the absolute value 2, and that's not going to change the signs of the number. The absolute values don't change. So that's going to be no change. So for all the values of x that are to the left of 1, there's no change. Let's do the other side over here. I'm going to plug in 3 now. Both of these equal 9 and they're opposite, so they just cancel, and once again we end up with the absolute value of 2. So this one also has no change. How about the middle? All right, so that's going to be 2.25 minus 3 times 4.5. And here we end up with negative 2.5, and the absolute value charts will change the signs from a negative 0.25 to a positive. So here we actually will change. So for all x less than 1, we have no change. For all x greater than 2, we have no change. But for all x in between 1 and 2, we will have a change. So now we're ready to write out our piecewise function here. Here we go. We have all x less than 1. We have all x between 1 and 2. And then we have all x greater than 2, and you can put the equal signs in the middle there because absolute value functions don't have holes, gaps, or jumps, so we can have an equal sign there. Now, what we said was that for all x less than 1, there was no change. So the function is going to stay pretty much the same. And for all x greater than 2, the same thing. This was no change. But for all x between 1 and 2, there was a change. And so all the signs on this particular function that was inside the absolute value bars, anything that was inside the absolute value bars will change its signs. And so all those ones are opposite signs. Okay? And so that's the first thing I wanted to do to begin the problem. But that's review. We've done that before. But it's been a while, so I figured we review it. So what do we do again? Let's review that really quick. Step 1, set the inside equal to 0 and solve. You'll need to use factoring. What that does, in essence, is it finds the cusps, the place where the pieces of the function connect together. Then we do the number line test, where we take those two values of x, put them on a number line, and we test numbers to the left and right of each of those numbers, and we decide does it make a change or not. And that way, when we write this as a piecewise function, we get rid of the absolute value bars, and for the ones that had no change, we leave the inside as it was. And for those that do have a change, like the ones between 1 and 2, we change all the signs of everything that was inside the absolute value bars. So that's how you change an absolute value function into a piecewise function. It's been a while since we've done that. So now that we've done that, I'm going to ask you guys a few other questions here. So let's go ahead and do number 2. I'm going to ask you guys to find the following expression. I want you guys to find the slope, g prime of x, from the left of 1. Well, since I'm coming from the left of 1, that's where x is less than 1, so I would be using this piece. But mind you, I want to find the derivative this time. So I'm going to take the derivative of that piece. So the derivative of x squared minus 3x is 2x minus 3. And then we're going to go ahead and do our direct substitution there, which is going to give me 2 times 1 minus 3, which is negative 1. So there's my answer. So the slope from the left of 1 is negative 1. All right? But let's do another question. What if I was asked to find the slope from the right of 1? Well, since I'm coming at it from the right of 1, I'm looking for where now x will be greater than 1 since I'm coming at it from the right of 1. And that's right here. The statement is saying basically that x is greater than 1. So I'd be using this piece this time. But now since I want the derivative of that piece, it's going to look like this. The derivative of negative x squared will be negative 2x, and the derivative of positive 3x will be positive 3. And then we'll do our direct substitution once again. And now I end up with a positive slope. Okay? So as you guys can see, if I were to ask you guys this question then, find g prime of 1, what we would say is, well, that's basically asking what is the slope when x equals 1. Well, the problem is, since the slope from the left and the right aren't the same, the slope doesn't exist there. So we're going to say it does not exist since the limit as x approaches 1 from the left of the derivative is not the same thing as x approaches 1 from the right of the derivative. Okay? So there is no slope at that point. Now, let's repeat the process, but this time, let you guys do this one. So this is going to be 5, 6, and 7. I'm going to ask you guys to find the following three things. I want you guys to find the slope from the left of 2. I want you guys to find the slope from the right of 2. And then I want you guys to see if you can find the actual derivative at 2. All right, so pause the video here, give those things a try, and see what you get. When you unpause it, you'll see the solutions. All right, and so there's your answers to 5, 6, and 7. I'll let you guys study that up a little bit. And then I have one more question I want to ask about this before I give you guys your student practice for the day. I want you guys to find g prime of x as a piecewise function. Okay. So pause the video here and give it a try and see what you guys get. Oh, actually, you know what? I'm just going to do it for you. I was going to have you guys do it, but you might need a little help. Well, how do you find the derivative? Well, you find the derivative of a piecewise function the same way that you usually find a derivative. You just take the derivative of everything, right? But the one thing we have to be careful with, which is what we talked about in a previous lesson, is that when you take the derivative of each of those pieces, if it's not continuous, if the derivative doesn't exist at certain points, then we have to leave off the equal signs. So in this case, since the function wasn't differentiable at 1, and it also wasn't differentiable at 2, you guys are going to notice that I no longer have my equal signs here. So that's the one thing we do. Now, another way we could write this derivative is using our rule. Instead of writing it as a piecewise function, the derivative rule from chapter 1 is this. You just take the original function, put it underneath of the same thing but without absolute value bars, and then multiply it by the derivative. Okay, those are both ways to write g prime. They're actually equivalent expressions, but this one is written as a piecewise function, and this one is using the rule from chapter 1, but they both work. All right, and then we have one more. I'm going to let you guys do an entire problem now from beginning to end on your own. Here's your student practice. I'm going to call it h of x, and it's going to be the absolute value of 8x minus x squared. I want you guys to find, well, actually, I'm going to say rewrite this as a piecewise function. I want you guys to find the derivative from the left and right of each cusp, like I did. And then I want you guys to also write h prime of x as a piecewise function and using the rules from Unit 1, just like I did. Okay, so same exact stuff, just all together in one big problem now. Go ahead and pause the video, and when you guys unpause it, you'll see the final solution. All right, guys, so here is my work. We have part A, where you set everything equal to 0 and solve. I end up with 0 and 8. Here's my number line test, which means that for anything to the left of 0, I had a change, and for anything to the right of 8, I had a change, but for anything between 0 and 8, there's no change. So we take our original function and rewriting it as a piecewise function. For anything to the left of 0, we change the signs. For anything to the right of 8, we change the signs. And anything between 0 and 8, we don't change the signs. So there's my piecewise function. And that's the end of part A. Part B, find the derivative from the left and the right of each cusp. Well, my cusps are at 0 and 8. So we want to find the derivative from the left of 0 and also from the right of 0. And I just realized I have a boo-boo on there, so let me fix that. There we go, I fixed it. So finding the limit from the left and right of the derivative of the pieces would look like this. And finding the limit from the left and the right of the derivative of the pieces at the other cusp, 8, would look like that. And so when you take your derivative, once again, you just rewrite the piecewise function with the derivatives, and you get rid of the equal signs. And I didn't write the rule from Unit 1, but if you did, it would have looked like this. And there you go. So those are 2 different ways to write the derivative. All right, guys, that'll end our lesson for the day, and we'll see you guys next time.